Hi friends, today I am giving a lecture on example problem on solving non-homogeneous or non-linear recurrence relation. In the previous videos, we are already solved 5 different example problems on the same topic. Now in this video, we have to solve another different example problem on this topic. Okay. Solve the following recurrence relation. A suffix n plus 2 minus 10 into A suffix n plus 1 plus 21 into A suffix n is equal to 3n square minus 2 for n greater than or equal to 0. Here, after equal to whatever the content is there, so that content is nothing but, that information is nothing but f of n. Okay, so here f of n value not equal to 0, hence we can say that it is a non-linear or a non-homogeneous recurrence relation. Okay, next one, on the left hand side, it is not in the standard form. Okay, so first we have convert into standard form. Okay, then we can say that this recurrence relation is a second order recurrence relation or not. Okay, so before going to that, this is the given recurrence relation, so that is equation 1. So what is the general solution for the given recurrence relation is non-homogeneous or non-linear? The general solution is, so A suffix n is equal to A suffix n power h plus A suffix n power p. So this is equation 2. Okay. The general solution for the given problem is denoted by A suffix n is equal to solution of the homogeneous recurrence relation, that is A suffix n power h, plus solution of the particular solution, that is A suffix n power p. Here we have to find out this value and this value. After we are getting that two values, we have to combine them using plus. Then we are getting the general solution of the given recurrence relation. First, we have to find out this value. Okay. So to obtain A suffix n power h, okay, put f of n. F of n that is 3n square minus 2 is equal to 0 in equation 1. In equation 1. So now the above equation 1 becomes A suffix n plus 2 minus 10 into A suffix n plus 1 plus 21 into A suffix n is equal to 0. Okay, so this is equation 3. Okay, next substitute n is equal to n minus 2 in the place of n in equation 3. So substitute n is equal to n minus 2 in equation 3. Okay, now it becomes A suffix n plus 2 is nothing but n is replaced as n minus 2. n minus 2 plus 2 minus 10 into A suffix n minus 2 plus 1 plus 21 into A suffix n minus 2 is equal to 0. Okay, now we are getting minus 2 plus 2 cancel, that is A suffix n, minus 10 into A suffix n minus 2 plus 1, that is n minus 1, plus 21 into A suffix n minus 2 is equal to 0. So this is the equation 4. Equation 4. Okay. Next one. So this is in the form of second order recurrence relation, n term, n minus 1 term, n minus 2 term. So these three terms represents the given recurrence relation 4 is in the form of second order. Okay. So equation 4 is second order homogeneous recurrence relation. Second order homogeneous recurrence relation. Okay. Hence the characteristic equation of equation 4 is, okay, what is characteristic equation here? Cn k square plus Cn minus 1 into k plus Cn minus 2 is equal to 0. Okay. So here after substituting it becomes n greater than or equal to 2. Okay, here n greater than or equal to 0. In the place of n we are substituting n minus 2. n minus 2 greater than or equal to 0. That is n greater than or equal to 2. Okay. Now what are the coefficient of c suffix n? So c suffix n is the coefficient of a suffix n in equation 4. So therefore c suffix n is equal to 1. Next one. What is the value of c suffix n minus 1? C suffix n minus 1 is the coefficient of a suffix n minus 1. So that its value is minus 10. Next one. What is the value of c suffix n minus 2? C suffix n minus 2 is the coefficient of a suffix n minus 2. So here that value is 21. Okay. Now these values are substituted in equation 5. Okay. The above values are substituted in equation 5. The above values are substituted in equation 5. So then what we are getting? In the place of Cn we are substituting 1. So that is 1 into k square. Next one, in the place of c suffix n minus 1 we are substituting minus 10. So minus 10 into k. Next one, in the place of c suffix n minus 2 we are substituting 21. So is equal to 0. Okay. Now k square minus 10k plus 21 is equal to 0. It is in the form of quadratic equation ax square plus bx plus c. So here now we have to find out the roots. So here 21 into 1, that is 21. 21 can be written as minus 7 into minus 3. Okay. So that is k square minus 7k minus 3k plus 21 is equal to 0. Next one, k into k minus 7 minus 3 into k minus 7 is equal to 0. So that is k minus 7 and k minus 3 is equal to 0. So then k is equal to 7 comma 3. Okay. So here therefore k1 is equal to 7 and k2 is equal to 3. Okay. Here the given two roots are different roots. Okay. The given two roots are real and distinct. Real and distinct. So we go for case 1. Case 1 is whenever the given two roots are real and distinct, then we can go for case 1. What is the general solution? So a suffix n power h is equal to a into k1 power n plus b into k2 power n. k2 power n. So here a into k1 value is 7. So 7 power n plus b into what is k2 value? k2 value is 3 power n. There is no problem whenever k1 is equal to 3 and k2 is equal to 7. There is no problem at all. Okay, then here a into 3 power n plus b into 7 power n we are getting, and we are changing these two values. Okay, so this is the a suffix n power h. So this is the homogeneous recurrence relation solution, that is the a suffix n power h. So this equation can be treated as 6. Okay, so next one, to obtain a suffix n power p, to obtain a suffix n power p, comma, put f of n is equal to 3n square minus 2 in f of n is equal to 3n square minus 2 in equation 1. Okay, then what we are getting? So that is the a suffix n plus 2 minus 10 into a suffix n plus 1 plus 21 into a suffix n is equal to 3n square minus 2. Okay, so here we have to observe that on the right hand side of equation 1 has the polynomial of degree 2. Okay, the right hand side of equation 1 is 3n square minus 2 has a polynomial of degree 2, and the LHS side of a given recurrence relation has the two roots 7 and 3. Among the two roots there is no value of root is 1. Okay, so now what is the a suffix n power p is? So a suffix n power p can be taken based on the right hand side of a, f of n is 3n square minus 2. Okay, here it has the polynomial of degree 2. Okay, so and the LHS side of the given recurrence relation has the two roots 7 and 3. Among the two roots there is no value of root is 1. Okay, so now 1 is not a root of characteristic equation on the left hand side of given recurrence relation, and the RHS side of a given recurrence relation has the polynomial of degree 2. So then the particular solution a suffix n power p can be denoted as this one. Here a naught is for constant, a1n is for nth term, a2n square is for polynomial of degree 2. So here on the right hand side it has the polynomial of degree 2, hence we can say that we can go for up to a0 to a2n square. So then it becomes the a suffix n power p is equal to a0, this is for constant, this is for nth term, and this is for polynomial of degree 2, polynomial of degree 1, polynomial of degree 0. Polynomial of degree 0 is constant, polynomial of degree 1 is nth term, polynomial of degree 2 is n square term. So here polynomial of degree 2 is there, hence we can go for a0 plus a1n plus a2n square. Okay, so now this is equation 7. Okay, this equation 7 can be substituted in equation 1 whenever a suffix n is there in equation 1. Okay, here this is equation 1. Okay, here a suffix n plus 2 is there. Here a suffix n value is this one. A suffix n plus 2 is nothing but whenever n is there we have to substitute n plus 2. Okay, so then equation 7 is substituted in equation 1. Okay, so now it becomes a suffix n plus 2 is nothing but a naught plus a1. In the place of n we are substituting n plus 2 minus plus a2, here n plus 2 whole square. Okay, this is the first term. A suffix n plus 2 is nothing but a naught plus a1 n plus 2 plus a2 n plus 2 whole square minus 10 into a suffix n plus 1. In the place of n we are substituting n plus 1. So that is a naught plus a1 into n plus 1 plus a2 into n plus 2 whole square. Next, plus 21 into a suffix n. So what is a suffix n? This value. A naught plus a1n plus a2n square is equal to 3n square minus 2. 3n square minus 2. Okay. Now we have to simplify that equation. So here a naught plus a1n plus 2a1 plus a2 into n plus 2 whole square can be written as n square plus 4 plus 4n. Next one minus a naught plus a1n plus a1 plus a2 into n square plus 4 plus 4n. Next 21 a naught plus 21 a1n plus 21 a2n square is equal to 3n square minus 2. Okay. Next one, equating the same coefficient terms based on the power on both sides. So see this one. First of all, a2n square. Here 21 a2n square. Here a2n square. 21 plus 1 22. 22 minus 10 a2n square. 22 minus 10 means 12 a2n square. Okay, on the right hand side only 3n square is there, equating only square terms. So that is 21 plus 1, 22, 22 minus 10, that is 12. 12 a2n square is equal to 3n square. N square cancel, a2 is equal to 3 by 12, that is 1 by 4. Okay, so next one, nth term. Here a1n is there. Next one, here a1n is there. Minus 10a1 plus 1 a1, that is 9a1. 9a1 plus 20a1 minus 9a1n plus 21a1n, that is 12a1n. Okay, next one, a2n. So a2n is here minus 40a2n, here plus 4a2n. So minus 40 plus 4, that is minus 36a2n. Here n is common, remaining 12a1 minus 36a2 is equal to 0. N goes to 0. 12a1 minus 36a2 is equal to 0. Here a2 value is 1 by 4 is substituted, that is 36 by 4 is 9. 12a1 minus 9 is equal to 0. 12a1 is equal to 9. a1 is equal to 9 by 12, that is 3 by 4. So a1 is equal to 3 by 4. Next one, constant term. So constant term, here a0 is there, here minus 10 a0 is there. So that is minus 9 a0, minus 9 a0, minus 9 a0 plus 12 a0. That is minus 9 plus 21, that is 12 a0. Yes. Next one, a1 term. So here 2a1, 2a1, here minus 10 a1. So that is minus 8 a1. Okay, minus 8 a1. Next, a2n. So, a2n is nothing but a2, only a2. So here a2, 4a2 is there, minus 40. So minus 40 plus 4, that is minus 36a2 is equal to, after RHS side only constant term is minus 2. So minus 2 I am writing. So here a2 and a1 values are substituted in this place. Then we are getting a0 value is 13 by 12. Okay. So now, after getting a0, a1, a2 values are substituted in equation 7. Okay, so then we are getting equation 8. So now we are getting a suffix n value and a suffix n p value, a suffix n power h, a suffix n power p value. Now these values, so that is equation 6 and equation 8 are substituted in equation 2. So equation 6 is a suffix n power h, equation 8 is a suffix n power p. So that is a suffix n is equal to a suffix n power h plus a suffix n power p. Okay, so what is a suffix n value power h? So that is a into 7 power n plus b into 3 power n. So this is a suffix n power h value plus a suffix n power p value is 13 by 12 plus 3 by 4 n plus 1 by 4 n square. Okay, so this is the final solution of the given problem. This is the homogeneous recurrence relation solution. This is the particular solution. When we are combining them, we are getting the final value. A suffix n is equal to a into 7 power n plus b into 3 power n plus 13 by 12, 3 by 4 n, 1 by 4 n square. So in this way, we have to solve the given problem. Here the most difficult is equating the terms on both sides. We can carefully observe what are the polynomials is there on the right hand side. We have equating the polynomials on both sides. That is most important. Okay, so thank you for watching this video. If you like this video, please share this video to your friends and classmates. If you like this video, please subscribe my channel name. So Divvela Srinivasarao. Thank you.